Hi, welcome to today's webinar. So as we've said, this is on low-cost connectivity and a DIY monitoring system, and it is focused around the system that we have deployed for monitoring of coolant on a machine tool. I'll be the speaker for today. So I lead on the machining side of the machining and additive team at the National Manufacturing Institute of Scotland. So a little bit of housekeeping just to begin with. This webinar is being recorded and it will be made available on our YouTube channel later on. Microphones and webcams are off during the session to avoid any background noise, but you will be able to type any questions that you have through the chat tool. At the end of the session, we will review some of those questions, so we'll have time to answer those questions at the end. And after the webinar, if you wouldn't mind, please take the time to complete the survey that will be sent out. So what is the National Manufacturing Institute of Scotland? The National Manufacturing Institute of Scotland is a group of industry-led manufacturing research and development facilities where research, industry and the public sector work together to transform skills, productivity and innovation to attract investment and make Scotland a global leader in advanced manufacturing. What will MMIS do? MMIS will increase productivity by reducing barriers to innovation, stimulate investment and increase manufacturing competitiveness, catalyze job creation and strengthen supply chain links, inspire and attract talent and equip current and future workforces with the skills that they and businesses need, and work with manufacturing businesses of all sizes in multiple sectors, providing benefits across the whole of Scotland. We are operated by the University of Strathclyde. We are part of the wider Catapult network. That's a network of research centres across the UK. And we are supported by our 8 partners listed on this slide here. At NMIS, we are a community. We are a combination of core capabilities that consists of specialist technology centres and an active network of partners within the manufacturing community. So our specialist centres, the Advanced Forming Research Centre has been around for quite some time now. Some of you may already be familiar with that. We also have our Lightweight Manufacturing Centre, our Digital Factory, our Manufacturing Skills Academy, and we have the wider capability network that we work with. So with all that out of the way, I'll jump straight into the main topic of the day. So to start off with, you might ask yourself, why should you monitor digitally? So within manufacturing, there's a large number of tasks that require manual checks on a regular basis, whether that is maintenance on machine tools, going out and checking a pressure gauge on an argon tank, checking oil levels, or checking the condition of your coolant. All of these are manual tasks that consume valuable time. They will add to your costs, and they are generally non-value add tasks in the sort of traditional manufacturing sense of non-value add, but they are still essential and there are definitely reasons for them. So first, the first reason to go digital is to try and reduce some of these manual checks, because if you can take a check out in the first place, then you eliminate that manual effort. But the second reason that you might not think of is to change the mindset on data. With the nature of these checks being manual, it can become quite monotonous and become part of the sort of the day-to-day task. You carry out the check, you write down a number on a table on a piece of paper, and you never think about it again. So what you end up with is a big stack of documentation that you're putting all this work in to generate, but you never really go back and look at or use until it comes around, until a health and safety audit comes around or some other audit comes around, and you need to dig back through this data. And then all of a sudden you find it's in someone's handwriting on a piece of paper, and it's hard to get all the numbers out. It's hard to make use of that data for any practical purpose. So by digitizing data, you can have a more robust historical data set. You can look back over that data and you can see what has happened. It's also easier to use that data. So again, rather than looking into a large table of information, you're able to display that. You can put it into spreadsheets, you can pull it out into other data analytics tools, and you get a general change in mindset on the data by changing it from just a task that you write, something that you read and you write down on a piece of paper and you forget about, or you maybe take a corrective action if it's becoming near or out of tolerance. You can start to look back over historical trends. You can start to see when stuff is drifting away, drifting out of nominal, and you can take corrective action earlier on. And you may start to see things that you didn't notice before. So I think the key takeaway at this point is just to consider, even if you're still doing a manual check, digitally recording that manual check might still be transformative for the usability of that data that you're collecting. So to start off with any monitoring solution, you have to identify what you want to monitor. In this particular case, we're using the example of a coolant monitor, but when it comes to low-cost connectivity, this could be anything around your workshop. Um, so within this particular example, where you want to start with is you want to identify what your key indicators are. So what the main things that you want to measure are, and then what secondary parameters, what sort of additional things might be of interest. So if any of you have worked with machine tool coolant before, you probably know that one of the main things that you check is the concentration. That's the dilution of the coolant product in water, as it is in the tank in the machine. That's traditionally done with a refractometer, and you can get digital refractometers as well. And that's important to control because if that starts to go out, if you have too much, you're using too much product, you end up with grease and oil all over your components. It ends up being a bit messy. If it goes too low, you can have corrosion, you can have bacteria growth, you can have all sorts of problems that can affect health as well. The next one is the pH. So the pH is an indicator of when stuff starts to go bad in your coolant. It's a pretty important factor for health and safety. So if your pH is out of where it should be, you can start to get dermatitis and other issues with the operator. You can also end up with bacteria growth. Now, bacteria can end up being the cause of the change in pH, but it can also be accelerated to change in pH. So you need to take regular dip slide tests and check that if there's bacteria growing in your coolant. And then the other one is level. So that's just how much coolant is left in your machine tool. Is it starting to run low or is it getting too full? So those would be the main ones that you might immediately think of. But when we started looking into it, we thought of a couple of secondary parameters. Obviously, coolant is a liquid. Its job is to keep your machine cool. Therefore, it is actively taking heat out of the part. We wanted to see how temperature fluctuated throughout machining operations and how temperature and humidity fluctuations may affect the other parameters that we see within the coolant. Now, the reason that we picked coolant in the first place as our topic for this was because we worked with the health and safety executive and they highlighted coolant as being one of the things that a lot of companies struggle to manage properly. They tend to find poor record keeping and a general lack of the proper attitude towards coolant. So we wanted to deploy a digital system and we focused on a low cost digital system that would be usable by SMEs and companies that don't necessarily have a very big budget to spend on it. But we wanted to try and transform that mindset, get them back to thinking about their coolant rather than leaving it to be something that their coolant supplier comes in and checks. Okay, so now that we know what we want to monitor, the next question is, how do we want to measure that? So the first thing to consider when you're looking at how you measure something is, again, bearing in mind that we're talking about digital in this case, is there some kind of a digital sensor that is available to measure that parameter? Once you've identified what sensors are available, your next question is accuracy. So just because you can get in an indication from or some kind of an electrical signal to indicate something, it doesn't mean that that signal is accurate or giving you any valid information. So you need to verify that what you're getting is good. Now that accuracy is relative to your application. Same with metrology, you select the appropriate measurement device for the tolerance that you're measuring. In some cases, you don't need to be exactly quantitative with your measurements. You might get a qualitative indication of what's happening within your process that is just as useful as the quantitative one would be. You have to consider the longevity of your sensors. So again, one of the reasons we're deploying these sensors in the first place is to try and reduce the number of manual checks that you have. And if you have to continually replace and repair sensors, then it doesn't give you any benefit. You might as well just take the manual recording and record that digitally. The next one is the calibration process, which is related to longevity. So how long does it take to calibrate it? How much downtime have you got while you're doing that calibration? How complicated is that calibration process, and do you need expensive equipment to achieve it? And how often do you need to do that calibration process? Again, going back to the theme of if you're doing manual checks, you're trying to replace them. If you're replacing them with something that you have to keep going out and manually calibrate, it doesn't give you the benefit. And then finally, we have the cost. So if there is a sensor is available that checks all the boxes, is it actually affordable? So running through the parameters that we have for coolant, temperature, humidity, those are quite simple. They're very common. You've got sensors in your phone that will give you temperature and humidity. You get ambient air temperature, and you can also use things like thermocouples to get more in-depth temperature in more sensitive locations. Uh, for the level is something that could potentially be a challenge. In our case, we were lucky that our machine has a float on it. So it's a little yellow piece of plastic that moves up and down on a linear rail or a linear slider. And all we had to do was put a distance sensor below that to see how far away the float was. So that allowed us to calibrate out and get a pretty good measurement of the level on the machine. And again, here's where accuracy is relative. I don't need to know, has it moved by 0.1 of a millimeter? It's got about 15 centimeters of travel. So, within a few millimeters is plenty of accuracy to get an indication of whether your tank is running low or sitting high. Next, we come on to pH. So pH was a bit more challenging. There are pH sensors available, but what you will find, they may be reasonably accurate once they are calibrated, but I've marked them down on accuracy because, again, we're looking at the application of a device that you can fit and leave in your coolant tank and not have to worry about too much. And if you don't continually maintain it, then the accuracy wanders. So these pH sensors, with them being so sensitive, they end up being, you store them in a pH neutral solution. You calibrate them before every single use and you clean them off after every single use. So for something that you're leaving sitting in a tank, it doesn't really tick the boxes for accuracy, longevity, and calibration processes. Similar with the concentration measurements. Now, we did end up getting a solution for concentration, which I'll come on to shortly. But you can buy digital refractometers, and again, the process with a digital refractometer, you need to keep it clean, so you make sure you're getting a good measurement. It's a reasonably expensive piece of kit, and it becomes more of a manual check again because you have to go out to the coolant tank, take a drip of coolant, drop it onto the refractometer to get your measurement. You don't get that sort of mechanical, automated pumping action of pumping coolant over it and just taking continuous reading. So that meant that we couldn't just buy an off-the-shelf refractometer and put it into our tank. And then finally, bacteria. It didn't seem like there was anything available that can directly measure the bacteria within coolant. The traditional process for this is to take a dip slide and they bring it to a lab and they basically grow the bacteria in the lab to see what is present on that sample. We did have a partial solution to this, but it's more of an indicator. But I'll come back to that as we go through the solution. So once you've identified what you want to measure and you know that there are means of measuring it, the next thing is to have a look into the commercial solutions that are available. So the benefits of going with the commercial solution, it should be established and proven. These will be sensors and devices that are out in industry working day to day, and you're going to get a reliable measurement from it because it's been proven. It should be plug and play usually. So again, with it being an off-the-shelf system, usually these things are quite plug and play. You don't have to do a whole load of configuration and programming and setting it up. And the same goes for the maintenance. If you've gone through a subscription process or some kind of a support contract, then that will be included. That maintenance should be included as part of it, and it should be a reliable and robust system. The challenges you might have, though, with going with the commercial solution, they can be quite high cost. When we looked into coolant with the focus on SMEs, we found systems on the order of tens of thousands of pounds per machine, which is not really viable and wouldn't be beneficial enough to justify removing the manual process. And you probably still need to have some manual processes in there anyway. They might only be a partial solution. So as with anything, when you look at the off-the-shelf solution, it's been there to address a particular problem. Maybe that doesn't meet all of the needs that you have for your solution. That's not necessarily a problem. And in fact, the solution that we have deployed, we do use some commercial solutions, but we mix them in with our own DIY system as well. So it's a matter of making sure you get the right spread of solutions to cover all of your needs. And then the next one is data ownership. So if you buy a system from another person, the way to think, I was trying to think of the cloud as being someone else's computer. So really, when if you send information to the cloud, all you're doing is sending it out of your network to someone else. A lot of these systems will provide tools to allow you to access that data, and the tools that we have deployed, we are able to get in and access your data and download our data. But if you are deploying a commercial solution, you might want to check the data protocols that are allowed for you to get to your data, and the data downloadability, and also the longevity of that. So are you only able to access data for the last 30 days? Are you able to access it fully historically for the life of the system? If you ever can end that subscription and hand it back, are you able to get your data out at the end of that process? And then finally, we have some systems might be proprietary and closed or restrictive. So sticking with the example of coolant, there may be a provider that will sell you a digital monitoring solution, but they may only provide it for their system, for their coolant, or there might be a machine tool manufacturer that will only provide something that integrates with their machine tools. And if you have a large workshop and you've got a range of different machine tools, a range of different products, you want something that will cover all of them. You don't want to be tied into a single application. If you wanted to consider the benefits of a DIY system, some of that is in reverse, but you do also have a lot of drawbacks potentially with a DIY system, which we'll go into as we go through our solution. So what did we end up deploying? We started off by deploying a liquid tool. Now, at the time of the trial, this was still in development. We got a free trial of this device and we put it on our machine. It only gives you temperature and concentration. So it doesn't give us bacteria, it doesn't give us the pH. Those were two of the things that we were interested in. So this is an example of one of those partial solutions, but what it does well. So it measures it gives us the temperature and concentration. We have local data access through OPC UA, so that covers that data access question. But they also have a cloud application. So if all you want to do is review the condition of your coolant, you can just log into their online portal and you can see the parameters that they've uploaded. But if you want to build your own system, you can plug in an OPC UA and you can pull that data out and link it into your system. Because it's a proprietary system that goes to someone else's cloud, it's easy to set up and use. You just plug it in, connect it to your Wi-Fi, and the data goes off, and you log into the platform and you see your data. It allows manual entry of additional data. So on the app, you are able to go into it and add in, if you take a manual pH measurement, for example, you can add that in. And it's not supplier specific, so we can use this with coolant from any coolant supplier. And in fact, their web app is already set up to help you with the refraction correction factors for the refractometer for different products. The other deployed system is a little bit different. So again, the reason we wanted to investigate coolant condition was because of a prompt from the health and safety executive and the fact that they had noticed that a lot of people are not necessarily compliant on it. And that raised the question of what else around the machine should we be monitoring that is related to coolant. So we spoke to one of our members, Fluid Maintenance Solutions. They provide a sensor system called the Operator Environment Module. They do provide some solutions that will go into coolant tanks as well and give you different information. But in the interest of health and safety for this particular project, we like to look at the Operator Environment Module. So this gives you a whole range of different parameters. In particular, there's the particulate matter mass concentration, and that is intended to monitor when you're machining and your coolant is running, you can get a mist inside the machine tool. When you open the door, that mist comes out into the air. So you want to know what that mist consists of in terms of particulates, and this gives you a good measurement of exactly how much of that your operator is breathing in. The design of the device, it's powered by USB 5 volts, so all you need is any 5-volt power supply, and you stick it to the front of your machine in the area where your operator is working. So that means that whatever the operator is breathing in is the same as what this device is measuring. It also gives you hydrogen sulfide. Now, I mentioned that we can't directly measure bacteria, but what hydrogen sulfide does is give you an indication, because that hydrogen sulfide is the gas that the bacteria in coolant will give off, and that's what some people might refer to as the Monday morning smell when you come into a workshop that has coolant that's been sitting over a weekend, or if you've got coolant that's getting a bit old and not in good condition, you might start to pick up on hydrogen sulfide. Now, as I said, this is over on the front of the machine where the operator is standing. So in this particular case, it doesn't give us a strong indication of what's happening in the coolant tank. But as I said, they have separate sensors. So if you wanted to put something in the coolant tank, you could use that. It covers noise level as well, and temperature, pressure, and humidity. So that's atmospheric temperature, pressure, and humidity. You can get a bit of an indication of what's happening in the workshop in general. Again, the data is free to download, so it all connects up through Microsoft Azure. there's no configuration with this device. It was literally a case of stick it to the front of the machine, log in on the app, and you can see all your data coming through. And then with all the data, we can download it. But through these solutions, you may have identified that we've covered a lot of what we wanted, but we didn't cover absolutely everything. So that left a few parameters that we wanted to measure. So if we move on now, we can have a look at the DIY solution that we deployed. This is probably, if you've looked into Internet of Things and you've looked into industrial solutions before, you've probably come across some of these Raspberry Pi based solutions that use Arduinos as a microcontroller to talk to sensors, and then use a Raspberry Pi as a host. And that's what we ended up settling on in the end for our particular deployment. Just within the scope of the project, it was what we could achieve within the time constraints that we had. We do have some follow-on work that I'll bring up later on. For now, though, I'll just give a quick overview of the system. So we have a Raspberry Pi, which is a small microcomputer. It's a single board computer. You can see in the picture on the right here, it's a very, very small board, but it runs full Windows or full Linux distribution on it. Because it runs full Linux, we have access to the USB COM port, so we can do normal USB comms. That lets us talk to our Arduino. We have an Ethernet connection, so we can plug it into our network, and it has the software stack to allow us to run Node-RED. So Node-RED is a data flow application that allows us to direct data from multiple different sources and pass it around our network and do what we want with it. So you can think of the Raspberry Pi as basically being the main controller that handles our information and provides our data collection and dashboarding. The Arduino is a small microcontroller, and it's a much more simple device. It can't run a full system. It can't connect to our network directly. Which is why we needed to use the Raspberry Pi. But to that Arduino, we've plugged in a BME680, or in this case, it was actually a BME688. Similar sensor. They're about 16 pounds. It's a little board that gives you temperature, pressure, humidity, and it also gives you VOCs. So that's volatile organic compounds in the air. We have a thermocouple so that we can directly measure the coolant temperature. So the BME680 is measuring the air temperature, whereas a thermocouple, we can actually sit into the liquid of the coolant and measure the coolant temperature. We have an ultrasonic sensor, so that's what we ended up using for distance sensing, and it has proven to be quite robust and reliable on the machine. It gives us an accurate enough measurement. And we did try a pH sensor, but I would say save your money and stick to the pH test strips, because it's more hassle than it's worth trying to keep that calibrated and maintained. So the Raspberry Pi running Node-RED allows us to have a local dashboard. So in the Node-RED data flow system, you can link up to your data sources, and then you can direct that to various different end paths. And one of those is a dashboarding system. Now, this dashboard is hosted on the Raspberry Pi, so you need to log into that IP address on your shop floor system, and you'll be presented with this dashboard. But it is quite quick to set up, and the data is available at a glance. So anytime I log in, I can see the data. The drawbacks that we have with it, though, is that it doesn't have a long-term record. So the graphs that you can see on the right-hand side, the dial indicators are showing the current levels, and we do have a bit of a historical graph, but that is only stored in the memory of the Raspberry Pi. That is not a long-term database. You can't go back and review what it was weeks or months ago. It's also a single point of failure. So if this Raspberry Pi fails, not only have we lost all of our sensors, we've also lost our dashboarding platform, and we've lost all of our data. So that leads us on to a bit more of a comprehensive architecture that allows us to pull the data out of that system and transfer it around our workshop. So on the left-hand side, you can see the Raspberry Pi, which hosts the Node-RED data flow software. And we have our Arduino. One of the benefits of the Arduino actually is that it can talk with it's as a microcontroller. There's loads of libraries available online. You can plug and play most sensors into it, and they can talk over protocols like SPI or I2C. So that BME680 sensor that we plugged in, it was as simple as loading, including the BME680 library directly from Bosch, and having it write out the values that it read onto the COM port. You can also do 0 to 5 volt analog inputs, and you can do digital inputs. That then gets passed to Node-RED. Node-RED reads that over the COM port and formats it and sends a message out over MQTT. So this is where MQTT is what lets us transfer the data throughout our network and get off of that local dashboard. We still have the local dashboard as a backup, but this means that we can now transmit data throughout our network. If you've looked into IIoT before, you might have encountered Factory Plus, which is based on Sparkplug, and that's kind of a specific implementation of MQTT and a structure around MQTT to make it work. So the sort of the background structure is a similar idea. This is just a more basic version. So on your office side of the network, you then have a PC or a server. A server is just a PC running software, but we install Mosquitto MQTT broker on it. So that's the MQTT broker is what handles the messaging protocol. So this sends out this publishes a message to the broker, and then the Node-RED data flow on the PC or server subscribes to that message and receives any messages coming through. So every time we take a reading, Node-RED parses that reading, sends out an MQTT message, which then gets received by the broker and passed through to this Node-RED data flow on the PC. That then writes it into InfluxDB, which is a free and open source database software. So we can install that database. It's a time series database, and it's very extensible. You can you don't have to define, like in SQL, you normally define large tables. In this, you just have to define the structure of your measurement, and you can write your measurement in. So you can add to that at any time in the future. You can also add historical data into that, which is of interest for some other machining IoT applications. And then finally, we have Grafana. Grafana is a dashboarding application. It can hook into various different databases, but it's quite commonly paired with InfluxDB. So we can directly pull out information from InfluxDB. So I have a screenshot here of the coolant measurements that we were getting through on InfluxDB. One thing I realize I've missed actually that I should have mentioned on the Arduino system, this Node-RED data flow is also capable of talking to the Liquid Tool device over OPC UA. So we don't just get our Arduino USB signals, we can also pull in our OPC UA data signals. And if we have a machine tool with MT-Connect or other protocols, we can pull whatever we want in and we can format it, and then we can send all that out as a message. So it allows you to combine multiple different data sources together. So this dashboard then presents all of the information that we need. So the benefits of this, it is a long-term storage solution. You can go back and view historical data. You can set the time period at the top here to whenever you want to see and see all of the data for that time. You're able to pull in data from multiple different data sources. So if you do have a live connection to your machine tool and you wanted to see when M8 was commanded on your machine, you could have coolant commands listed. As an example, because we're talking about coolant, you could have the high pressure, whether it's high pressure or through spindle coolant or whatever parameters you want, and look back historically. It also is more suitable for use in data analytics applications. So it has, with using InfluxDB, it's got the query language. You can, you'd be better off speaking to our digital team around data analytics, but they would be able to pull information from the database and do whatever analytics they need on that. So the drawbacks that you have with this DIY system is probably quite apparent to a lot of you. You need to understand how to write the Arduino code. You need to understand how to set up a Raspberry Pi. You need to have the network infrastructure to be able to pass the data around to your system. And you need to maintain a server and a database on that system. So the DIY system does give you a lot of benefits in that you can read a whole lot of information, but you do obviously have that quite considerable overhead for setup and for maintenance going forward. So that's pretty much as far as we got to with that particular project. We have identified some things that we would like to do. You probably noticed, if I just jump back to the slide, this is not an industry-ready solution. You would not want to leave this on your shop floor for any length of time because it is not robust. It is an experimental setup intended to test the functionality. It is not intended as a final product. However, there are products available that are very similar. So the BrainBox's BB400 is an Arduino and a Raspberry Pi, but it's in a DIN rail enclosure, so it's industrialized. I think it takes a 24-volt input, so you can potentially add that to your electrical panel on the back of the machine if you are confident in wiring that sort of thing in. And then there's obviously the Siemens logo and other PLCs. You could use a PLC to read a lot of this information, and there are some relatively low-cost options for those as well. So you don't have to spend an absolute fortune on a very powerful PLC to do this basic monitoring. But one of the challenges that you might have when you look at some of these PLCs is the sensors that we had use I2C or SPI, and these are microcontroller communication protocols. A lot of PLCs won't speak those languages natively and won't be able to directly interact with those. So you may have some challenges, and you might have to find alternative sensors to give you the same readings that will give you a different output to the PLC. I've already mentioned the potential to expand the solution. So again, we use coolant as the example for this webinar, but it could apply to a whole range of different things that you want to measure on your machine tool. And within the machining team, we have got connectivity to multiple machines. So throughout all of our machines, actually, we either have MT Connect or we will have OPC UA or MQTT. On our FANUC controller machines, we use a FANUC flow gas adapter to get an MT Connect stream out of the machine. On our DMD machines, we have the IoT connectors, which provide MT Connect, OPC UA, and MQTT, but it's all for quite low frequency data. But again, as you can probably see with Node-RED, we are able to just talk to that and pull the same data in and put it into the same database. We also have the Spike Map software, which is something that we newly installed in our DMU 125. That talks directly to the machine controller and pulls out relatively high frequency information, and that gives you parameters like the spindle current, position data, lines of NC code, that kind of thing. And in addition to that, we have various other data sources within digital machining. So we have Spike tool holder, which gives us torsion, bending moment, and torque on the tool. So you can see the amount of force that is being applied in cut. We also do tap testing, which allows us to measure the resonant frequencies of the tools and identify when we expect chatter to occur. And we're working on a smart fixturing system, which will allow us to collect data in process. So when you think of the overall data collection system, you need to think of not just your current application, but future applications and expandability of where that data can plug in. So that's quite a lot of information. That is the end of the presentation. I'm sure we'll have a few questions, which I'm happy to answer now.
Thanks very much, Connor. That was great. There's not any actual questions put on the chat at the moment. There was one comment put on earlier from Alistair. pH sensors have been developed that are solid state and don't require calibration or wet storage. And he kindly provided a link for that in the chat box. Okay, and also mentioned there are other suppliers.
Okay, that would be really good to see.
Okay.
But we did, I'd be curious to see the longevity on those as well. When we were initially researching it, we did find one or two of these companies that provide these sensors that did say they had challenges with the longevity of pH. So I'm keen to try that. Thanks, Alistair.
Okay. Steve Thompson is just on for our sensing system, Connor. We now have touchscreen for additional manual data entry.
Yep, that's true. Actually, I believe we are going to be getting one of those sensors quite soon, actually, Steve. So just to add on to the previous slide on the fluid maintenance solutions box, we mentioned manual data entry to upload data to the liquid tool system, but that is also available now on the fluid maintenance solutions box.
Okay. And Steve has just added on issue with submersive probes and coolants is oil contamination.
Yeah, so there's various different challenges with coolants and the types of contamination that can come into them. You've got various different types of swarf, you've got different sizes of swarf, you've got the potential for bacteria growth, and then you have all the various lubricating oils within your machine tool that can end up in there. And that kind of forms that nasty stuff that you get on the top surface of your coolant. So you can get skimmers that will skim some of that out. Yeah, you need to be aware of this. And it comes back to the manual data checks that we're doing. So if you're doing a weekly manual check, does your sensor allow you to extend that to be every 2 weeks or maybe every month? Or do you still have to do all of your manual checks? So it's something that you need to assess on a case-by-case basis when you are deploying an IoT solution.
Okay, that's great. Thanks, Connor. I don't see any other questions on the chat box at the moment, but obviously Connor's email address is on the screen at the moment. If anyone does have any questions afterwards, by all means get in touch with him. Sure, I'd be happy to help. And if that's us finished now, we'll just bring the webinar to a close. I'd just like to thank everyone for joining us today, and thanks to Connor for providing today's webinar. Thanks a lot.
Okay, thanks.